Hey guys, I want to talk about kinematics today. Kinematics is the study of motion. It's usually the first little part that people look at in physics. It's all about how things move, where an object is, when it's going to get somewhere, how long it takes to get there, how fast it's moving at any point in time. A lot of neat things. We move every day. Everything is moving. The Earth is moving. The solar system is moving. You're moving. Cars move. All of that stuff. And so motion is a really important thing. We usually start physics with that. You've only got 5 variables that we try to measure when we think about motion. And here are the 5. You've got something called displacement, which is distance. It's the distance away from the starting point. So if you start here and you move 20 meters that way, then your displacement is 20 meters. If you move 40 meters away and then move back 20 meters, that would be a total distance of 60 meters. But you're really only 20 meters away from home. Your displacement is that distance from beginning to end. The initial velocity, V naught, is the way we say it. Naught is an old-timey way to say 0. So at the beginning of the problem, the initial velocity is V naught, and the final velocity would be the speed at the end of the problem. And acceleration is A. That's measuring how fast you're speeding up, how fast you're picking up speed or losing speed. And then lastly, you've got time. Well, the units are really important in physics. You need to watch these. You need to know what they are. You need to know that displacement gets measured in meters and acceleration in meters per second squared, because then when you see a problem and there's a couple numbers in there, you might have 17 seconds, 4 meters, and 3 meters per second squared. You can read the problem and see what's going on, but that second tells you that this is a time, and that the meter tells you that this is a displacement, and meter per second squared has got to be an acceleration. It's like a name tag. You just look at the unit and it tells you what these things are. Now, of course, there are 2 meters per second, so you got to say, well, which one's at the beginning, which one's at the end. The context of the problem should tell you all that. There's only 5. You put them in the right box and label them. And that's always your first step. I'll show you an example here in just a second. Let me show you the formulas first. There are only 3 formulas. There are 5 variables. There are 3 formulas that tie those 5 variables together. And when you think about it, they make perfect sense. Right here, the final velocity, how fast you're moving at the end of the problem, is going to depend on how fast you were moving at the beginning of the problem, plus any extra velocity that you pick up by accelerating for a period of time. Okay, so that looks pretty okay. Right here, the displacement, how far you travel, is going to be, it's going to be equal to the initial velocity times the time. When you move at a velocity per time, that covers distance. So this is the x that you travel because of your initial velocity. And if you're accelerating, that's going to make you go farther. If you're speeding up, you're covering more distance. So this is some more x that's due to acceleration. When you add those together, you get the total x, the total displacement right there. That looks okay. Right here, v squared equals v naught squared plus 2ax. Another formula. This one's really nice because there's no time factor. See how that one's got a time? You got to either know the time or be looking for time. Same here. But this one, if you get a problem that doesn't have time in it, that last one is your buddy right there, and you need to grab onto that. So let me show you how these work real quick. I've got a airplane accelerates from rest to 52 meters per second at an acceleration of 6.2 meters per second squared. Find x. All right. And some people like to make a little list. Some people like to draw a little picture. It's all up to you. To me, a picture is absolutely the best thing. If you can see this, if you can make it real, here's an airplane right there. And the airplane's going to move over here, at the beginning of the problem initially, and final over here. I can see that. I can understand a plane going from here to there. So when I look at the problem and I'm looking for numbers, I'm looking for the information, 52 meters per second, 6.2 meter per second squared. Find x. That's a number 2. That's the displacement. I've got 1, 2, 3 numbers. They gave me 2. They're asking for a third one. Now, if you come down here and look at this, 1, 2, 3, 4. V naught, AT. That formula has 4 variables in it. I only got 3. 1, 2, 3, 4. I've already got t, so that's 4 in that one. 1, 2, 3, 4. All of those, you have to have 4 variables. We only have 3, so we need to go back and look at it one more time. Oh, here it is. Accelerates from rest. That's actually a 4th number right there. At the beginning, it was at rest. The initial velocity was 0 meters per second. The final velocity is 52 meters per second. The acceleration all along this way, we sped up at 6.2 meters per second squared, and x would be that distance, the displacement from here to there. So I'm going to just put x equals question mark. Now you don't have to draw the picture if you don't want to, but I do need you to be able to go through and get the numbers and say that's in meters per second squared. I know that's acceleration, and to find all those. Somehow you need to have on tap v0, a, v, and x. Okay? The next step of this thing would be to go through your list of possible formulas here and see which one you want to use. There's only 3 of them, so it shouldn't take too long. But you could come in here and say, well, I've got the final velocity, I got the initial velocity, I've got the acceleration. Oh, time. I don't want time. I want x. This is not the variable that I want. Now, I could solve this equation, right? I could find that. That is mathematically possible to do, but it's not going to give me x. X isn't even in that equation. I'm trying to find something that has v0, v, a, and x. Let's look at the second one here. Got there's the x that I'm looking for. I'm put a little mark there. That's what I'm trying to question mark. That's what I'm solving for. So that's looking good. I got v0. Oh, I don't have t. See how there's 2 unknowns in this one? It is mathematically impossible to solve one equation that has 2 unknowns. So that is not the one we want today. I look at the last choice, say v, v0, a. There's the one I want. See how there's only 1 unknown? And it's the one I want. I could solve the first one. And if you really want to get fancy, you could solve this top one for t and then put it in here and here and get x that way. These equations are consistent. They work together. It doesn't matter if you go this way or that way. As long as you keep the rules, you're going to end up with the right answer. That's a beautiful thing. But I'm going to use that last equation. You always want to write down your equation so that everybody knows where you're starting from. You're saying, this is my starting point. I want x. So now you need to do a little bit of algebra. And you know there's only one rule of algebra, right? You can do anything you like as long as you do it to both sides. So if I'm trying to leave x here, I want to get rid of the v0 squared. I want to get rid of the 2. I want to get rid of the a. That would leave, somewhere down here I'm hoping it says x equals number, x equals formula, x equals stuff over there. All right? So I need to move things around. And typically we get rid of this addition subtraction stuff first. If I come in here and subtract v0 squared from both sides, then v0 squared minus v0 squared is 0. That's gone. And I'd have something that looks like minus v0 squared equals 2ax. Okay? Remember we said we want to get rid of the 2 and the a. Those are multiplied. The opposite of multiplication is division. So I want to divide by 2a. Cancel the 2, cancel the a, nothing but x left. Got to do the same thing on the left-hand side. That's my formula. That's the version that I want to start putting numbers into. Take your formula and work it into the specific solution here before you go jamming numbers in it. It's less writing, it's lazier, it's easier, and this is still true for every problem in the world. Okay? So, to me, that's worth something. I've got all my numbers up here. I made this nice little list so that I can say, well, I need v. V is 52. And I want to put the units on there because they're going to keep me straight. v0 is 0. I could just leave that one off because subtracting 0 squared isn't going to change anything, but I'm going to put it in. Here's 2, and a was, 6.2 meters per second squared. All right, I got my numbers in now, and that's going to be x. I need to put all that into my calculator. You got to learn to talk the language of the calculator here. So let me do this for you here. Preparatory to starting, preparatory to pushing buttons here, I'm going to put in some parentheses. I want that whole numerator to happen before I divide by 2 and divide by 6.2. You get two choices on this at the bottom. You could say, well, I'm going to put some parentheses around the bottom. I want the entire top to be divided. That fraction bar there says divide by everything on the bottom. So there's two ways to do that. I'm going to show you both ways. You can pick whichever one you like. But I'm going to start with that blue parenthesis right there. Forget about the parentheses around 52 because there's nothing else in there. Here's a squared. I'm going to put the minus 0 squared, but you understand that doesn't really do anything. And there's the whole numerator, tied up in parentheses. Okay. Then one choice will be, say, divided by parenthesis 2 times 6.2. And you can close that off if you want. I get 218 meters. That's the minimum length of the runway. If you want this airplane to take off, and if it needs to go 52 meters per second, and if you can only accelerate at 6.2, you better have 218 meters of asphalt sitting there for the airplane. Okay, otherwise it ends up in the ditch or upside down or something, and that's generally considered bad. Now the other way you could have done this is you could have gone 52 squared. Tell you what, let me just leave the parentheses out of the numerators. We could forget about the 0 squared. That means I've only got one thing, so I don't really need to get too fancy. There's my 52 squared, and I could say divided by 2 and also divided by 6.2. I'm dividing by both of those, and I'll get exactly the same number. What you do not want to do, though, is do 52 squared divided by 2 times 6.2. Remember that Aunt Sally taught us our order of operations? We're looking for parentheses, no parentheses. I'm looking for exponents. It's going to square 52. I'm looking for multiplication and division on the same priority rung, step 3 of this thing. So it's just going to do all the multiplication and division from left to right. It's going to square 52. It's going to divide what you get by 2. And then whatever you get there, it's going to multiply by 6.2. That is not what we want. Okay, that'll give you a wrong answer every time. So I'll be happy to work some more of those if you want, but be careful with that. Anytime there's two things on the bottom, your choices would be to say divided by parenthesis first thing times the second thing, or you can say divided by A and also divided by B. Okay, but not divided by A times B. You got to learn to speak the calculator's language, and that's one of the things that people trip up all the time. Okay, got this special kind of problem called a cliff problem. A cliff problem arises any time that you're standing on top of a cliff or a building or a hot air balloon or something, and you've got something in your hand, and you throw it or shoot it or something. Maybe this is a cannonball, and they shoot the thing off, and it's going to fall in a path like that. We call that path a trajectory, and it's going to land somewhere over here. Okay. The first thing that you have to do on every cliff problem, and I call it whatever, if a wheel falls off an airplane, it's going to make that same path. Whatever it is, I just call them all cliff problems. You got to separate out the known variables into the x and y directions. You want to break apart all the components of these things. So the thing is going to travel some distance to the right. Okay. This x right here would be the displacement in the x direction. So it's going to, essentially it's starting right underneath here, and it's going to go that far to the right. That's x. I need to know how fast it's moving in the x direction. I need to know what the acceleration in the x direction is, and typically that number is 0. The reason it's 0 is because gravity does not pull sideways, so I definitely don't want to put gravity's number there. And once it leaves my hand or the cannon or my foot or whatever this is, it's not going any faster, right? I'm no longer pushing on it, accelerating it. So usually the acceleration in the x direction on cliff problems is 0. If you had a rocket, if you had a parachute, something weird like that, it could be different. But typically in introductory physics, it's not. And there's some amount of time that it takes to travel from here to there. Now that's going to be the same amount of time it takes to move sideways and the same amount of time it takes to move in the y direction. So this is in both lists right there. But other than that, these have nothing to do with this. We're separating them. There's a line between them. And the x direction and the y direction have nothing to do with each other. Okay? Treat them separately. Now, in the y direction, I'm starting up here, and I'm going to come down here. So there's my y. Some speed up and down. This one looks like it's horizontal. So the v naught y there is 0 the way I've drawn it. If you throw this thing sideways, it's not going up or down when you throw it. I'm only interested in the up-down variables. And up here, I'm only interested in the left-right variables. Okay, or the pieces of the variables, the components of those vector quantities. So I need to know that number. I need to know a sub y. How fast is it accelerating down? Well, that's gravity. That's where the 9.8 meters per second squared goes. So I got to separate all that out. X and y, a sub x, a sub y, v naught x, v naught y, right there. That's step one. Instead of having one list of numbers, you got two lists of numbers, and you can write them separately if you want. But there they are. Okay, these four, those four. The second step is always use the displacement formula in x and y direction. Okay, that's a total lie. It's not always, but it's usually use the displacement formula. That was number 2. Remember, that was either x equals v naught x t plus 1/2 a sub x t squared, and then the other one would be y equals v naught y t plus 1/2 a sub y t squared. It's the same dumb formula, but we just replaced all the x's with y's, and we put these little extra x's there to say I only want the x component of the initial velocity, and down here I want the y component of the initial velocity, and same for acceleration. Okay, so we're going to use those two formulas. There are some problems where they say how fast is it, and what's the velocity at the bottom. And there you'd use the velocity formula instead of the x formula or something, but usually it's like this. So let's do one. Right here, a rock is thrown horizontally 6 meters per second. Ooh, meters per second. I recognize that as a velocity. This is some kind of velocity. Oh, it's not when it hits. It must be at the beginning. This is v naught. But that's not really good enough. I need to break that out into v naught x and v naught y. If I throw it horizontally, all the motion is left-right. It's x direction. So I'm going to put a 6 meters per second right there. And then the y, if it's going horizontally, it's not going up-down at all, so that would be a 0 meters per second. Okay, we got this number figured out. Here's the next number, 20-meter high cliff. That's my y. And it might be useful to note that that is 20 meters down. When I think about this picture, like that, and here's this rock, and I throw it that way, with the initial velocity horizontal, the rock is going to fall in that fashion, which means it started here, i.e., and it's going down. It's going to end up down below where it started. Okay, so that's my y number right there. They want to find two things, the time and the range. Okay, so we're going to use those two formulas. I'm going to work in the y direction to get time. That's going to look like this. I take my y formula. And see how there's a 0 there? Anytime you can put a 0 in, say v naught y equals 0. 0 times t is 0. All that goes away. Makes solving this so much easier if you kind of dismiss some of the parts, send them off to recess or something. I'm going to come in here and do a couple things all at the same time. There's a 1/2 I'd like to get rid of, and that tells me that I want to get rid of this 1/2. If I multiply on the left by 2, then the 2 times the 1/2 is going to cancel. If I do it over here, I got to do it over here. I want to get rid of that a sub y. So if I divide by a sub y, then the a sub y on the top will cancel the a sub y on the bottom. Do it on the right, got to do it on the left. Okay? That gets me down to t squared. We crossed off everything except for t squared. And on the left-hand side, I've got 2y over a sub y. I don't want the squared, I just want t, and the opposite of squared would be square root. So I'm going to come in here and take the square root of both sides. That's doing the same thing to both sides. And the square root cancels the squared, and I've just got t. Okay? That's what I want to put my numbers into. Solve your equations for the variable you want, and then you can put the numbers in there. In this case, I'd have 2 times 20 meters times a sub y, divided by a sub y was 9.8 meters per second squared. Notice how I'm putting the units in so I can watch them and make sure it's behaving itself. You get a choice here. This is 20 meters down, the y, and a sub y is gravity pulling down 9.8 meters per second squared down. Those both pulled down. They're both in the same direction. So they either need to both be positive or both be negative, and it doesn't make any difference which. Usually I recommend that people come over here and draw some kind of arrow that I'm going to call a coordinate system. And you just arbitrarily pick one direction to be positive. Let's say up is positive. Most people seem to be more comfortable with that. Okay? So if everything that points up is positive and this is down, then it gets a negative sign. There's a big old negative sign. And this is down, opposite direction. Opposite gets a negative sign. Okay? So down here I would need to put in a negative sign for both of those. Like that. And then on my calculator I could handle that. I can find my cursor. There it is. I'd simply go square root, second squared, see the little square root right there, 2 times negative 20 divided by negative 9.8, and I get 2.02 seconds. Now, I could have called both of them positive. If I had run my coordinate system the other way, I would have gotten exactly the same answer, seconds. How do I know it's seconds? Because I like to watch the units, and here's what I mean right here. On the units, I've got square root of meters over meter per second squared. That's a compound fraction. So I need to invert and multiply. I'd have the square root of meters times second squared over meters. The meters are going to cancel. The square root of second squared is seconds. Okay? When you go to the 2.5 seconds of extra trouble and you see that the unit comes out right, you get a big grin on your face. You get the big warm fuzzy feeling because you know you did your algebra right, and it just confirms that everything is flying straight. Okay, that was the time. So we've done this one. To get the range, I want to work in the x direction, and I'm looking for x. And once again, we're going to use the displacement formula, this time in the x direction. Looks like that. Remember, we like to get rid of the zeros. I guess I wrote it here. I wrote it on the last screen. A sub x is 0. Do not put 9.8 right there. Gravity does not pull in the x direction. It does not pull sideways. It pulls down. So all I have to do here is say v naught x, which was 6 meters per second, and multiply that by the time. I just found the time. Come up here, and I'm going to put that in, 2.02 seconds, and I'm real close to 12 meters of range here. In fact, you may just want to put that 12.12, okay? But at some point the book's going to want you to round it off to some number of significant figures. So I'm going to just put 12 meters. Notice the seconds cancels the seconds, nothing but meters left, right? Watch those units. They're your friends. They will help you. All right, I got one more thing here for you. The last kind of problem that we talk about in kinematics typically is the level ground problem. Okay, now I want to remind you that the cliff problem looked like this, where something started up here and it ended up down there. Okay, on the level ground problem, something starts right here and it goes up and it comes back down on level ground. Okay, now they don't always tell you it's a level ground problem. Sometimes you just kind of assume, but if they don't tell you there's a cliff, there's no cliff. All right, if there's a cliff, they got to tell you about the cliff. So if it's level ground, let's say you're on a football field and you kick a football, right, and it goes up and it comes back down. There's going to be a couple numbers there of interest. You're going to kick that football at some speed, some initial velocity, and there'll be some angle there. If I change the initial velocity, that changes how far it goes. We call this the range. And down here in the formula, they call that R. Okay? But I've got a formula that says how far it's going to go. I got a formula that says how long is it going to be in the air. I got a formula that says if you want a range, if I know that I need to send this thing 60 meters and it's leaving at 14 meters per second, it'll cook up the angle that I need to aim that thing. Maybe I've got a bow and arrow. All I can do is point up or down, right? This would give me the angle that I need to do that. So that's the level ground problem. You do not want to use these level ground problems on the cliff problems. You don't want to use them on regular kinematics, but they are fantastic here. Again, this is not a full version of all this. This is simply the quick and dirty version as a review, as a whatever. First look at it. A ball is kicked upward at 8 meters per second. That's got to be my initial velocity. 40 degrees, that's theta. They want me to find two things, the time and the range right there. Well, I come over here and look at my formulas. I got a formula for time, and I just stick the numbers in. 2v0 sine theta divided by g. It's already in the right form. We can put our numbers in. 2 times 8 meters per second times the sine of 40 degrees. Need to divide that by g. G is 9.8 meters per second squared. I don't have to get the x and y component. I don't have to worry about up and down and positive and negative. Just put the numbers in. All right, it's going to look like this. I have 2 times 8 times the sine of 40. And see how the sine started a parenthesis? I need to close that parenthesis and then divide by 9.8. You will get something totally different if you forget to close that sine. You will also get something different if you don't check your mode button from time to time. See how I'm in degrees? You don't want it set on radians. When you put degrees right there, 40 degrees, you need to be set to degrees. Okay, so make sure you're in the right place. But the time in the air is 1.05 seconds. And then they also wanted the range. We've done this one. The range, I go down and I get the other formula. And I'd write it down. R equals V0 squared sine 2 theta divided by G. So here I'm going to do 8 meters per second squared times the sine of 2 times 40. Double the angle. You can put an 80 here. You can put 2 times 40, whatever. But don't forget to double that angle. G is 9.8 meters per second squared, like that. And you do the thing. It says 8 squared sine 2 times 40. Close up the sine. Divided by 9.8. You should get 6.43. That was the range. Wonder what the unit would be. There's meters per second, which got squared. So that's meters per second squared. On the bottom, there aren't any units over here. I've just got meter per second squared. That's a compound fraction. And when I square meters squared and seconds get squared, I'd have that. I invert and multiply. So turn this guy upside down. Looks like that. The second squared cancels the second squared. The meter cancels one, but not both of the meters. So I got a meter left, and that would be my range. I was desperately hoping that the range would be measured in meters. It is. Everything's good right there. All right. So here's kinematics in a nutshell. Not the whole thing, but what you probably need to do to pass some questions and to get a passing relationship with this thing. You got 5 variables. It's always the same 5. You could have this list in the x direction and also 5 in the y direction, except the time would be the same. The units are really important. Watch those. You got 3 formulas. You could copy them again and say these are my x direction formulas and my y direction formulas. You could have z direction, right? If you had a 3-dimensional problem. We don't do that typically in first year physics, but you could see where since we live in a 3-dimensional world, it could become a possibility. Cliff problems. You always want to separate the known variables into x and y. You always want to use your displacement formula. Don't forget about the coordinate system. Everything up is one direction. Everything down is the opposite direction, so it gets the opposite sign. All right, and then you got your level ground formulas right there. So lots of fun stuff to think about. Hope that helps.